thank you so much, everyone, for taking the time out to meet up with us today. It's the 3rd of June, and this is ORI's FPGA Projects Meetup. And what we do is we get together and we talk about what we have done, what we have planned to do, if we have any roadblocks, anything that's getting in our way, and if we need any resources that ORI can provide or that we can help you in reaching out for from other organizations and other resources. And welcome to everyone gathered today. And I do have a quick report from Aaron. He's not able to join us today, but he did have a report about what he's been doing with the DVB-S2. This would be the downlink for our satellite project. And what he's working on is integrating it, and getting some better demonstrations going. So he has Everest's Pluto ORI firmware. So it's Pluto-based ORI firmware from F5OEO. That's his call sign, Everest's call sign. And Aaron reports that he's got it running on the Pluto SDR and controlling it through the MQTT commands. That's something that Everest kind of brought to this implementation. He took our VHDL encoder for DVB-S2 and implemented it and made it possible to configure it and control it over MQTT. So he's been able to validate transmit using the test tones, and next step is actually generating the data that it expects and feeding the encoder and testing the transmit. He's going to use the BATC Pico tuner as the receiver. This is something that he's talked about on previous calls, getting the Pico tuner up and running. And we're all interested in getting build instructions and user guides and more context and explanations, like why would you want to use this? What is it for? What kind of what does this fill in? What does it do? Why do you care? So we're gonna move forward on that. So big thank you to Aaron. KI5BAB is his call. So that's a report from Aaron. So he'll be back in the next couple of weeks. Okay, and then I have lots to talk about from our work in the lab over the past few weeks, but I'll pause here and let Pete take the floor because he also has a whole lot to share. His article just went out in the newsletter for May, our Inner Circle newsletter. And so yeah, Pete, you have the floor. You want to talk about the article or anything else that's on your desk?
Oh, sure thing. Thanks, Michelle. So basically the article's out, and maybe have a little more to talk about that in a week or two because I'm adding OTFS to it for part 2. But the other thing that's going on is a more practical waveform design for Eve, which is looking into just FSK and how we do that. So the thing that makes it special for Eve is that we have minus 8.6 dB C over N naught from our link budget, and we can only coherently integrate for a half second. So of course you see the problem right away is that ES on N naught, if you only coherently integrate for a half second, is like nearly minus 12 dB. And the bit error rate's going to be about a half, and there's no FEC code that can fight our way back out of that one. So it takes a little bit of simulation rounds to see if we do a whole bunch of half-second non-coherent correlations to get our symbol period up to many seconds, then what's our bit error rate, and how do we match that up to an FEC code? So that's the other thrust right now. Just develop a real practical, as simple as it can be, FSK waveform with an FEC code matched up to it. And the output of that, well, the inputs are our link budget and our coherence time from the Doppler spread study that CES did at Camera. And then the output would be what symbol rate can we achieve and how long does a burst need to last? And this is designed for, of course, the new goal at the next inferior conjunction of two-way communications, not just detection, but actual two-way amateur communications. But I think that's it.
Well, that's a lot. So yeah, that'll be your second article in a series about this type of communication, very challenging link that uses, some techniques that may not be as familiar as the traditional sort of communication techniques. But this is an excellent opportunity to and demonstration eve, which comes around every not that often, but the next opportunity will be October in 2026. And what we're doing is taking a real hard look at this very challenging communications channel, developing some techniques to try and to hit it again from as many different citizen science sites as possible. And DSES is one of them, but also Thomas Telkamp's, doing the low site. Stockert site, Bockham is also another potential site, and there's several others out there that are very interested in what was achieved this past March. And yeah, we're really looking forward to this. So thank you very much, Pete, for sharing your expertise. You're very accomplished in this area, and we really, really appreciate your time and energy in developing the articles and also developing the potential communications protocols. So these sorts of efforts what we do is we figure out how we can possibly get information over this channel. So not just a radar return. I think we have growing confidence in that our ability from the amateur and citizen science community that we can definitely bounce a signal off of Venus. So we've done it twice. Now the tougher challenge is to do communications. So being able to encode information on a transmission requires a higher performance sort of deal. So just the presence or absence of a carrier tone, good, got that. Now next step is, can you discern information, some changing symbols, changing aspects of the wave. And so that's the sort of things that Pete's tackling. Very tough communications channel. So we're all kind of working together in the community to make this possible. And thank you very much for your time. Hopefully you'll get lots of good feedback from the article and interest and some more folks reaching out to sort of increase the footprint, so to speak, of the folks involved for October of 2026. The more sites involved, the better. All right. Anything else?
No, I guess I just say that if anybody gets any great ideas with short block length FEC codes, I'm all ears because, of course, a short block length code that performs well might really help Eve. So I'm just kind of learning as much as I can about that. If anything comes to mind, let me know, please.
Okay. Definitely. We'll help spread the word. Okay. And then Daniel, welcome again. Very good to see you again. And if you have any comments, questions, any work to share, or anything you are especially interested in, you have the floor.
Hi, this is Daniel. I'm sort of trying to learn about voice over radio in highly restricted environments, and I think Venus might give an example of a very complex channel. So I'm trying to learn, starting from I'm an engineer, a computer science engineer, but not radio engineer. So it's an opportunity for me to stretch my mind, and I appreciate you guys letting me be part of the audience.
Yeah, well, welcome. And yeah, please feel free to ask any one of us any questions you have. This is what we would like to do is to make this as educational and supportive as possible so that you can take full advantage of all this cool stuff going on in digital communications. It's really a golden age for radio, and we're thrilled to get to work on this sort of stuff and share it with as many people as possible. It's kind of our job.
Thank you.
All right. So
Continue listening.
oh, sorry, go ahead.
And I'll just continue listening.
Oh, okay. Yeah. Please dive in at any point if you have any questions. Okay, Paul, I think you have the floor, and let us know what's going on.
Okay, well, first a brief remote labs report. Nothing to report in the remote labs, very brief. Um, Everything's up and running as usual. Not a whole lot of activity explicitly in the remote labs, but we're doing some work right next door in my lab. I guess I'll leave the introduction and summary of that to you. Michelle, go ahead.
Okay, yeah, this is I'll summarize a little bit of the work that Paul and I have done. Really appreciate your help, Paul. Could not have done this without you. And what you should be seeing on the screen is a diagram of what goes on with the Opulent Voice protocol. As of today, so some of this has been implemented and is working, we're going to say over the air, but it's really over the LAN. So what we've done is we've done a lot of work on a modem, on a FPGA, and this is to take bit stream, zeros and ones, and turn them into minimum shift keying, and to be able to transmit and receive minimum shift keying symbol using like Hodgart and Massey techniques. So these techniques date back to the 1970s, 1960s, 1980s. This minimum shift keying is really cool. This is a tremendously awesome, modulation scheme. It is the right answer for what we are doing. It's constant envelope, and really very, very groovy. So lots of spectral efficiency. We're huge fans, and it is used in space quite a bit. So that's our motivation, is to provide a really solid, good uplink communications channel, the best possible choices that we can make for amateur satellite use and also terrestrial use. This is totally appropriate for terrestrial deployment for either point-to-point links or repeaters on Earth. So we'll be supporting both cases. And so after working on the modem for quite a while, this is work led and very ably led by Matthew Wishick. We've gotten to a point where we've tested it working over the air. So we have a pretty good, there's some things that are still, some action items, some things that still need to be done to make the modem truly perfect. There's some bugs in there. But for the most part, that's a working modem. So at this point, we now need to start making decisions about the upper layers of the protocol. So this is where you frame up your data. So as of today, we've been using pseudo-random noise sequences or pseudo-random binary sequences, PRBS, in order to confirm that what you send is what you're getting. So there's some really neat PRBS mechanisms going on in the modem, but it's just a stream of data. That's it. There's no framing, there's no protocol layers, there's no voice in there. Those things, the way that we want to do it is to say, okay, you have voice, you have chat, keyboard, you have a file, you have authentication, authorization messages. We want all of that to be handled in the same channel. We don't want you to have to switch to another packet mode for data. That's traditionally how it's been done in amateur radio. We don't really want to do that. We want it to be seamless and easy and modern. So that's our goal. And so we're getting there. And over the past week or so, we've been able to demonstrate this priority data handling in the lab. What we did is we said, okay, here's the modem over here on the Pluto, and we're going to start up a Raspberry Pi 4, and we're going to write Python, and we're going to do the framing and the handling of essentially the multimedia. So you want to drag and drop a file, you want to have keyboard chat, you'd like to have a push to talk voice on a USB headset. Good. Okay, so all of that goes into a Raspberry Pi, and the Raspberry Pi decides how to frame up the data. And now it presents it over Ethernet. Now you can take that to another computer and you can have a call. You can experience what it's like for a radio link, sending it to another computer. This allows us to really put the user interface and the decisions that we have made about the prioritization, about the quality of service decisions, the state machine that we have running, to a test. And we found a significant issue. So the authentication and authorization messages handling, and we call them A5 because it also is access and acquisition, so all of these control messages that you would need for a significant resource like a satellite, these are messages that have to happen in order to be able to handle setting up and tearing down sessions and calls and things like that. So we had those as the highest priority. And it became evident to us that that was probably not the best decision if we also want voice to never be messed up. So if the A5 messages interrupt voice, and if they happen to need to do a certificate, a crypto certificate to make sure that the person is authenticated and authorized to use the satellite, well, that's going to sound like crap. So went away and thought about it and decided, okay, voice really does need to actually be the very highest priority because that's the one thing that the human is going to notice interruptions of. And the second highest priority would be these control messages, and then chat, and then data. So reversing the top two, we had authentication being the most important and voice being the second important, chat and data. Well, if we reverse the top two, we eliminate this problem. What do we give up? A person that may not be authorized to use a satellite will get through with at least one voice transmission. We think that's an okay compromise. And to be honest, most repeaters, most satellites should pretty much take anyone and only enforce an authentication or authorization policy if there is a complaint or if the satellite needs to be used for only trained people in an emergency, for instance, or any other policy that the operator can come up with. So light touch is kind of what we're assuming, but we don't want these authentication and authorization messages to wreck the voice. And we did that. We changed it around, and we very little, damage, and then proceeded from there. Oh, go ahead, Pete.
Yeah, just a quick question. So, if the first voice transmission gets through under the scheme, how do you know on the second transmission that it's the same person? Could they change their credentials or something like that and then just have a whole bunch of first transmissions?
They could. There's lots of ways to game any sort of digital system. The way that the protocol is constructed is that every frame that you send from your station has a claimed token, and that 3-byte token is supposed to be checked. So Paul can probably address this in more detail. So I'll let him take over from here.
Yeah, that if the user is legit and is not changing his identity on the fly, then we can verify that at the receiving station. There, each frame contains a rather extensive header that includes the identity that you claim to be, which is a call sign encoded typically, although it could be anything up to about 8 or 9 characters from a restricted character set. Um, and in addition to that, there's a 3-byte token calculated cryptographically. Um, it's not by itself, it's not super strong, but it only has to be strong enough to last for 40 milliseconds. And it's computationally infeasible uh, to fake those. So if the base station or the satellite, in the case of the satellite system, wants to be absolutely sure, it can verify the token on every frame and not let even a squawk of data through. And that's true even in the case where we haven't done uh, or haven't prioritized the authentication reply message, which is the one that can damage the voice on the uplink, because the satellite is free to implement whatever policy it wants for letting packets through. If it decides that it absolutely can't allow um, any noise through from unauthorized parties, it doesn't have to. It can simply refuse until a valid authentication reply has been received. So that just means if the bad guy talks for a long time on the first transmission, he's just wasting his time and wasting uplink energy, possibly interfering, but we can't prevent interfering. Um, and if the satellite wants to be a little more open than that, but wants to prevent this rolling identity attack we were talking about, all it has to do is notice that there are a lot of authentication failures and step to a more strict policy for a while to thwart that fellow. So it's not 100% perfect in terms of what the damage can be done from a transmitter. but it's really hard to get any useful communication through the system um, if the satellite doesn't want to allow it. And I think that's such a huge step forward from where amateur radio has ever been before that it's worth doing and um, sufficient for our purposes. There's a whole paper on this if you want to read about it. There's a poster presentation as well. I think all this stuff is on the website or in the GitHub.
Yeah, I'll make sure it's findable. Link up to here. Oh yeah, that's thank you. That's a really good explanation. What I did here on the screen is a draw.io version of what's been on the whiteboard. So instead of showing the photograph of what's on the whiteboard, I went ahead and did this. What I did here, based on Matthew's feedback about concern about the amount of overhead of all the different protocol headers, is that I did this to scale. So each one of the small divisions, so this should look like graph paper in the background. But each one of the small divisions, I said, okay, that's a byte of data that's being sent. And t equals 0 seconds here is the start. So let's say you start up your system, you're at idle, and you want to hit either push to talk, which would be that's the sort of the bottom horizontal bar, so this is time along the bottom, and this is what's being transmitted in these blobs. Now, you see that there's two parallel things here. This is not being sent at the same time. It's a choice of one or the other because of the priority. So on the bottom here is 80 bytes of opus and all the headers that it would take. So if you imagine that you're at time 0 and you hit push to talk and you started talking, that you would go to the bottom branch of the tree here. So I know it's probably not as clear as it could be. This could probably best to have this in separate diagrams, but I just wanted to show the difference between, like, if you're talking voice, then look to the bottom bar here. And if you were you fired up your station and you sent out a chat message, that's what you're getting on the top, chat message, and then immediately followed by a file data transfer. And so that's what's happening here. And the file data may go out for quite a while. This could be many frames. But here, oops, I have a typo here. So this is 40 milliseconds, t equal 40 milliseconds. This is actually t equal 80. So this is only 2 frames worth of action going on. It's really, generally speaking, not going to be this busy. Your chat data is really short. It may only be some smaller number of bytes, smaller than 80 bytes of your voice packet, and you're not going to send out just a single voice packet. You're going to talk for quite a while. A typical transmission may be many seconds, maybe as long as a minute. So what I'll do is I'll keep working on this and draw up some things that sort of reflect real use cases, and then generate the use cases that we anticipate, based on actual times. But if you're just going to take 2 frames worth of data, this is what the headers kind of look like. This is how big they are. So for the voice channel, or for the voice priority, then we start out with our own headers, our own custom headers. It's about 12 bytes now, could be 15, but 12 at a minimum. Be great to kind of get down to 12. So those are our custom headers that for our particular communications, all this stuff is enabled by this header format. We have a synchronization pulse to help receivers that may not have a great clock. And so that's every frame. So we have a synchronization pulse. We have the station ID in every frame for identification, for sure. And then we have that cryptographic token that we claim. So you claim to be W5NYV. Here's your token. And then there's other flags that may need to go in there. For instance, whether or not this is the last frame of the stream. That's something we talked about quite a bit. We also had a bit error rate test bit in there, but we think that we can actually achieve bit error rate testing through the data file. So sending a particular data file, we should be able to get the statistics for a bit error rate test from that. So we don't need to spend a whole bit every single frame for that. But in terms of end of stream or not, that's good because in the case of a satellite, especially, you may fade out and your satellite is like, where are you? Did you stop? Was this the end of your transmission or did you fade out? How long do I keep the resource open? How much longer should I wait before I start searching again? And those sorts of questions from a system level are helped greatly by having an end of transmission or end of stream, uh, firm notification. So that's some of the things that are in this custom header for Opulent Voice. So let's say we're doing voice and we're Opulent Voice encoding. The payload is 80 bytes of Opus, but the first thing you get after the Opulent Voice headers is an IP header. It's 20 bytes minimum. It could be more, but I think that we can use the minimum. I think we can fit everything in there that we need. Next is UDP, which is always 8 bytes. Next is RTP, or real-time protocol. For voice, this is very useful at the application layer for handling what is essentially a VoIP call. So we're going to put that in there for now and test and see is it worth the 12 bytes to have it? That's always 12 bytes. We're always 80 bytes of Opus, and then you will hit your 40 millisecond frame boundary, and you will get another Opulent Voice custom header. And so if you're in a voice call, you'll get the exact same thing again. You'll get another, and it's all encased in COBS, constant overhead byte stuffing. So that's the encasing protocol that we use. And I think there's also a paper on why we pick this. COBS allows us to inform the receiver, anybody using this data, where the boundaries are. How much stuff are you getting? And everything gets a COBS, 1 byte header, and then it basically tells you where the next 00 is. So there's no zeros for constant overhead byte stuffing. And Paul, if you want to add anything here that might clarify why we're using COBS, why we would put that in there, go ahead.
Okay. Am I on? Yeah. The traditional way to do something like this is uh, a byte stuffing protocol like SLIP uses, or a KISS TNC. That worst case overhead for a protocol like that is nearly 100%. It's really terrible. Of course, that only happens when you have a certain data pattern. But COBS, consistent overhead, bytes stuffing, byte streaming, either one, um, is consistent in overhead, and they consistently very much better than that. Like 1 byte or 2 bytes is the worst case for a packet this size. Um, so we just decided to swallow that overhead and get framing that's flexible, so we can have lots of little frames, or many big, or 1 or 2 big frames, or whatever we need at the same percentage overhead, with possibly plus a byte. So that's the general argument. It's really simple. It's designed to be simple for software to do, but it's pretty simple for hardware as well. We we did a VHDL implementation of it, um, using Xilinx's block-to-block transfer interface, which is called,
AXI.
thank you, AXI, and AXI streaming. And it's a little bit more complicated in that case because you're trying to minimize latency, and the pipeline is complicated. But just some logic equations and a little bit of squinting and head scratching, and we had that going. That's pretty thoroughly tested in the can for when we need it, if we ever do. Um, One other thing I wanted to point out here is that this T equals 0 is not exactly when push to talk is pushed, probably, because we probably need an acquisition preamble. So this is at the end of the acquisition preamble, where we establish our timing for frames for this transmission. That's what T equals 0 means in this picture.
Yeah, good point. Thank you. Yeah, the preamble, which we assume that we're going to use, is something that the modem is going to add. That's our current plan. So yes, the T equals 0 seconds here is not exactly when PTT is pressed. It's at some point after that. Not very long after that, but yeah, this T equals 0 is where where our headers and our data flow pick up. So thanks. I'll I think I can include that in the next revision of the drawing to make it more clear. Okay. Oh, go ahead, Daniel.
Yeah, in other protocols I've seen, there's usually error correction of some type. Is
Yes.
there any, did I miss the part where the error correction occurs?
No, no, you haven't. So yeah, what we're doing here with the prototyping in the lab is without the forward error correcting from our proposed protocol yet. And so our discussions just yesterday actually were, are we at in the Raspberry Pi in the framer essentially, should we go ahead and take this task on? Should we go ahead and do all of the forward error correction, or should we have the modem do it? And Matthew is looking to see if there's room in the Pluto FPGA right now to where he can go ahead and do the, because we have two types of forward error correction. That synchronization pulse, or essentially a pilot tone, is unencoded. The rest of the header, that Opulent Voice custom header right there, that green block, the rest of that is Gole encoded. And like at 1224, something like that. It's in the paper. So Gole encoding for the header, and then a Viterbi encoder for the rest of the payload. So yeah, if we need to go ahead and do that, like we could do the forward error correction, we could continue and do that, and then do also the scrambling and the whitening as well, or we leave it up to the modem. So the division of labor there is still not exactly nailed down, but we are. Matthew seemed to be confident that the modem could handle all of that, and so that's kind of good in a way, because that means that the stuff that the Raspberry Pi is doing, framing up the data, making decisions about priority, what goes first, second, what's buffered up, what we've been able to demonstrate over the LAN, so kind of fake over the air, is really nice audio over the LAN appearing in the headset of the computer it's directed towards. And we've been also to demonstrate queued chat messages. So while you're talking on the radio, you can chat on the keyboard. You can type up like, oh, okay, I'm telling you about this cool website. And then you just cut and paste into chat terminal and hit enter, and it's queued up. And that chat's waiting for you to lift off of PTT, and then all your queued chat messages are go right out the door, right after your voice transmission, and then you're off the air. Now, if you also have a little a file queued up too, then it would follow the chat message out the door, and then end. So all of that working over the LAN, it doesn't need forward error correction. Well, no, because it's not going out over the air. So that may be a good division for an implementation for over internet. I know this is kind of controversial in amateur radio, so communications over the internet, not real radio. So the decision about how much to do in the Raspberry Pi is still kind of ongoing. But yes, there's forward error correction because we get a great benefit from it. And the decision of Gole encoding and the type of Gole encode and the type of Viterbi decoder are very typical for VHF, UHF channels. And they're also decent. They're good for microwave as well. So they match up well with the frame size and data rates and give us a benefit.
So if I understand correctly, the bit rate is very constrained. What is your target minimum bit rate for satisfactory performance?
Let's see, the bit rate, when we're talking about the bit rate of the Opus of the voice, is 16 kilobits per second. So you don't want to, you wouldn't want to do like too much music, although you can recognize music at 16 kilobits per second. So it's excellent voice quality. So that would be the bit rate for the voice channel.
Yeah, I think I am in ham as well, but I would need to say that for testing purposes and prototyping to make sure the system works, I see no problem with using wired connection to help with the debugging. That seems very logical to me.
Okay, cool. Always good to to get reassurance that your decisions are, sensical. Yeah, we do want people to use it for like the hotspot scene is pretty healthy, and I'm fairly familiar with like Repeater Builder and Jonathan Corgan's work with I think it's MMDVM. So we were talking about that yesterday. Like, can this fit into that? It may be too high bit rate or too large bandwidth for VHF, but for UHF, this is legal and would work. So there may be a minor constraint here, in that it may only be a UHF mode for the hotspots. But we would have to make it possible for the signal to work. We have to look pretty carefully to make sure that like a station, an MMDVM station, could handle minimum shift keying. If there's any particular restrictions there, like, is it's FSK, so an FSK system should be able to handle it, but we'll have to test and see. We have a lot of these stations here on hand and have a little bit of experience using them with different modes. So that's kind of an exciting way. It would get this out in front of people and they could hear the substantially better voice quality for themselves. And we think that that will cause a lot of excitement and happiness. So, and also, the fact that, if you use it from a Raspberry Pi, you can incorporate, all the things that you would expect. You can use your voice, you can send a chat message, you can share a file. And there's some control messages that are handled, and you don't have to switch modes or do anything weird. It's built in and it will handle all of that for you. We think that those are big advantages and will be of interest.
One little point. Um, right now, our baseline is fixed rate vocoder. We're always putting out 80 bytes every 40 milliseconds, regardless of whether we need them or not. Even if the speaker should hesitate and generate 80 milliseconds of silence, we'd still be putting out 160 bytes of data during that time. Um, and we'll proceed with that assumption for now and have the simplicity that it gives us. But the Opus vocoder is perfectly capable of going into a variable bit rate mode where it saves bits when it doesn't need them. And if that's the case, we can probably start playing tricks, like probably send our chat data in between in the silences of the voice. So I want to experiment with that, but not just yet.
Yeah, that's an exciting thing to take advantage of. Right now, what we do is we configure the voice channel to be a constant bitrate or CBR versus VBR. Those are two options that are in the Opus standard. And then we're fixing the bit rate at 16 kilobits per second, and that produces the 80 bytes of Opus reliably every time, whether it needs it or not. So that's our starting point, and it works and sounds great. But yeah, there's lots of optimizations and future complexities that we can do if it's possible to simply fold the chat channel or chat priority into a variable bitrate gaps, then that'd be pretty neat. So we'll see. And if there's anything else that anybody sees, any optimizations or cool stuff that they would like to try here, well, that's kind of the power of an open source protocol with a bunch of folks that are willing to say yes, we'll try it. So open invitation to look at this and think about it. What we're trying to do with the work over this past couple of weeks and definitely the next few weeks is to build it and try it at a relatively simple level. So, some of this is simplified or, blocky in a way, like, prioritization is one or the other. And we believe that that will get us further along faster and better if you just go ahead and build it and try it. So I think the bottom layer here, the lower level or lower floor is the audio, and that's pretty consistent. You'd get this IP, UDP, RDP, and then the 80 bytes opus over and over and over again, and every 40 milliseconds you get another Opulent Voice custom header frame. Okay, so that's what you'd have up here. There's some things that need to be addressed up here in the top. This is where the chat data and the file data would happen. The chat data, as of today, it gets an IP header and then a UDP header, and then the chat data encased in a COBS, constant overhead byte stuffing protocol. We may want to use TCP for this to make absolutely sure that your chat data gets through. So that's a kind of an open question right now. And then you can also have file data. Okay, so again, this is encased in COBS. That's what you get on the outer layer is always COBS. For file data, it'd be an IP header, a TCP header, and then the file data. The file data can go for a long time. It can go for many, 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 many frames. So an open question right now is, what do you do if you end and then you have extra time? So I'm voting for we just pad out the last frame of file data. It has to end on a 40 millisecond frame boundary. And then if you have a voice call that interrupts your file data, that voice call will start on the very next available 40 millisecond boundary. Now, this does mean that, you might be waiting for your voice for some time. And Paul has brought up that we want to have a very consistent experience for voice folks. Like, is 40 milliseconds objectionable? I'm okay with lining everything up on the 40 milliseconds. Pad out any data that you need in order to get there. And if you're, because humans are asynchronous, you may push to talk, and you've just missed the 40 millisecond frame boundary. And I think it's okay to wait for the next one, but we'll see. What we're going to do is, keep this, keep moving on and test this in the lab. And I think that actually demonstrating it, having a demonstratable system, something that anybody with a Raspberry Pi 4 and a computer and, or a receiving computer, as long as it can run the Python scripts, and as long as you have a USB headset and some way to, wiggle a GPIO on your Raspberry Pi 4, we could show you how to do that and how to set that up. As long as you have that, you can test this too. So the barrier to entry on using Opulent Voice should be as low as possible. And as more people that kind of use it and torture test it, the better at this point. So over the next couple of weeks, we're going to find out a lot more and try to enable as many other people to get it up and running and test this part of the system. So this is totally disconnected from the modem. The modem, we ship all these frames off to it over Ethernet, which means that your radio can be remote. So this station can be anywhere. And then another thing that is going to happen here, all of this is command line or terminal program in Python. There is a web interface, a HTML5 interface for this. So everything that works at the terminal will also work in HTML5, and it will be accessible as absolutely possible. So anyone, no matter who or what you are, can use it as easily as possible. So there's two sort of dividing lines or two big areas of modularity. There's a web interface. So as long as you have anything that can run a browser, any type of device that can run a browser that can talk to the Raspberry Pi 4, at this moment, a Raspberry Pi 4 running the Python script and running the terminal program, then you can interact with this sort of collection agent for your voice and your chat and your data. And then that Raspberry Pi 4 ships all of the frames to a radio over Ethernet. And it's another, marking line or separation line for the modularity of this radio system. So all of it together could be a pretty small package. If you needed to separate them out, like if you just wanted a command line interface and you just wanted to run it that way, you could do that. If you want to provide a nice HTML5 interface for the radio, that can happen. It bolts right up. If you need to separate the radio, put it closer to an antenna or have it in a fixed location, and then you want to carry your Raspberry Pi around, you can. So that's kind of the goal for this particular phase, is to do this. It's 3 major chunks. They can all be in one place, but you can also separate them out. And if you didn't like the HTML5 web interface and you wanted it to be more complicated and not so simplistic or sparse in design, because we are going to keep it as accessible as possible, then you can write a different interface. That's something that you could do. So if you wanted to have something very complicated that had access to everything or had lots of fancy graphics that may not be as great, for someone with a visual auditory, disabilities, then you can do that. That's totally possible. So that's kind of the direction that we're going in for this particular phase. This is essentially a prototype or first implementation. The modem target of the Pluto is a very powerful choice because it's so available and it's relatively inexpensive. Widely known in open source community. That part's working pretty well, and there's still things that need to be done, but it's now reliably working. I think we've had a link going, PRBS link going for weeks in the lab on the Plutos in the lab. So the work here is framing and some of the protocol decisions. There will be more revisions as we dig in deeper and find out that maybe some of our assumptions will not hold. For example, the A5 versus voice thing, that assumption turned out to maybe not be the best. There's going to be others in here too. So some of this may change. Kind of a question on, the question is, why do you have so much of this overhead, TCP, UDP, IP? Why not just have your custom Opulent Voice headers and then Opus or data? Why not? Well, because there's tremendous advantage that you get from having these very well accepted, time tested protocol layers. It allows application layer programs that we don't have to write to be able to consume this information. And also we can encode or tell these layers, like the size of the payload. We can tell it where does it go, what type it is. This gives us a tremendous advantage. So we believe that that's the case, and we're going to set out to prove it. If they don't pull their weight and it's just way too much overhead and doesn't give us a clear benefit, then we drop back to less layers, less overhead. So that's kind of the current situation, and the sort of the decisions that were taken on. These are the things that we've proposed and are building, and the next part is testing it over the air or over the LAN, as the case may be. All right. Any questions or comments or any other subjects? Let's see something in chat. Okay, yeah. So Matthew wasn't able to attend today, but he is the lead for the modem and also is the author of our modem module approach, which is writing modem is written in VHDL, targeted for FPGAs. And through his work, we've been able to have a really successful, very modular design. What it does is it uses sub-modules in GitHub, and you can then build a transceiver out of different modules. So this has worked pretty well for us. Sub-modules are kind of a tricky thing in Git, so it does take a little bit of learning. But what we've done is made it as gentle as possible. So the top level repository just pulls all these things, pulls all the components together, and then builds the bit file and builds the image. And then the instructions tell you how to install it on your Pluto. And then there you go. So working for us.
Have you got a minute after the meeting?
Oh, sure. Yeah, I do. Yeah, thank you everyone for listening to me. I did the best I could to kind of fill in the gaps and to make a a scale drawing of the overhead. Because when you see how much overhead there is compared to the data, it can look like a lot. But the advantages that you get from things like RTP, UDP, IP, TCP, IP are pretty big. So we tried to emphasize that in the most recent newsletter, and we'll keep highlighting that. Um, it can be tempting when you hear the word overhead that it's unnecessary, baggage that you're dragging along. Um, so we believe that the value that we get from going with these standard protocols are superior to us putting it into our custom headers or putting things into our custom headers and inadvertently limiting the flexibility of this particular communications protocol. So that's kind of our direction. That's our sort of the assumptions that we're making here, and we're going to essentially set out to disprove that. So, we're going to test it really hard and see if what we assume, what we believe is turns out to be true for this particular mode. Um, that's the challenge over the next few weeks. All right. Anything else, Paul? Did I screw up anything or miss anything?
I think you pretty much covered it.
Okay. Yeah. Thank you, everybody. Okay. So what we'll do is we'll close for the week and we should see you again in a week. This is our usual time to meet. And yeah, we'll hold one next week, if not before. So we might have an office hours if things change really rapidly over the next week, then might hold another meeting. And if anybody has anything that they want to share or they'd like to present, then just let me know and we'll schedule that for you and get the word out. All right, thanks everybody, and see you soon.